All right, so the wording on this one I put on here because I think wording like this is vague, so I want to make sure that we see an example of this because it does not. All the other ones that we've done have been they've basically worded to where you can identify what the null hypothesis is, and then from that they make a statement about what the alternative hypothesis would have to be. I don't know if that's what happens in this one when I read it. Okay, it says a company claims that the average time a customer waits on hold is less than 5 minutes. Okay, so I should say claims, not clams. So a company claims that the average time a customer waits on hold is less than 5 minutes. Less than 5 minutes. So when they say less than, what hypothesis does that belong with? That goes with the alternative hypothesis. Good. Okay. So I'm going to say HA. We're talking about average time, so we're talking about mu here, is less than 5 minutes. Okay. As we read through this, so it starts immediately talking about the sample 35 customers has an average of 4.78 minutes. Assume the population standard deviation for wait time is 1.8 minutes. Does it say anything here about H sub 0, the null hypothesis, what the established wait time already is? No. Okay? Which is a little bit different than the other problems that we've seen, right? So if they do that, it's fine. Okay? If we remember what we've always said about these two hypotheses, what do they have to be to one another? Complement. So if this is less than, this needs to be greater than or equal to. Good. Okay. And remember that this one here, okay, because it was the less than one, and we were saying that they claim that. Okay, that's our claim. Is it okay? All right. Now, I don't give you an alpha here, so let's decide an alpha. What? Let's do this. Let's do a couple different alphas. Okay, and see if anything happens when we change our alphas. Okay, and I don't know. There could be situations where if we choose different values of alpha, we do the same conclusion of the reject or not reject based on the data here. But I'm interested to see maybe something will be shown here. So let's go ahead and say, let's go with alpha. Let's go alpha equals 10%. Okay, so let's go alpha 10%. This is a left or right tail test. It's left. Remember the inequality sign here in the alternative hypothesis is going to point to the direction that the tail is in. So I'm going to put, let's just go to Z. I'm going to put sub 1.0 here, just to keep track, because we're going to change it to like 5% and 1% in a little bit, and we'll just see then if it'd be easier, right, as a subscript here, remember which Z-score goes with what. So 10% alpha, we have to figure out what is that Z-score attached to that. Okay, again, you can use your notes, okay, but if you don't have those, you can go always norm.inv. Probability that we're looking at, 10%. Standard deviation, 0. Sorry, mean, 0. Standard deviation, 1. And it gives me negative 1.28. Negative 1.28. And remember also that our null hypothesis should always be the mean here. Okay, that's the hypothesized mean. So anything that would be beyond this threshold to the left would lead us to a rejection of the null hypothesis. Okay. figure out that area there is the rejection region. So let's go ahead and run through our z-score for our data. Okay, which if you remember, that's x bar minus mu divided by sigma divided by root n. Okay. X bar is the sample mean. So what's our sample mean here? 4.78. What is mu? What's the average? Say again? Well, careful. That's a standard deviation. Yep, right here. Mu is always going to be right there in your null hypothesis. So -5. And then sigma, that's the 1.8. And we're divided by root. 35 people, 35 customers. Let's see here. So we'll run through that real quick on Desmos. So 4.78 -5. So negative 0.72. Negative 0.72. Leave your data negative 0.72. So in that case, where does that fall? Does that fall in the rejection region or the non-rejection region? Non-rejection. Okay. So we would say that we fail to reject the null hypothesis. We do not have evidence to support the claim that the mean is less than 5. Fail to reject the null hypothesis, do not have evidence to support the claim is less than 5. Now, here, and I've used, I gave you this phrase before. Okay, remember this is type 1, type 2 error. Type 1 over here, type 2. And this is to reject a null hypothesis that should have been accepted. And this is to accept a null hypothesis that should have been rejected. We're interested most of the time in type 1 error. And I'm using the word accept here, okay? But that's kind of a misnomer because when we say accept, we're saying that is like certainty. Like it is 100% the mean. Does that make sense? Okay. We're using the words reject or fail to reject, okay? And we say fail to reject. My hope is to always see that fail to reject does not equate to accepting. Does that make sense? Fail to reject just simply says we don't have evidence to the contrary. We don't have evidence to say that this is not the case, okay? But there may be evidence out there that has not been used or discovered or whatever that may lead to the contrary, okay? But our sample is not providing that evidence, okay? If you had me in geometry, like if I gave you these two triangles, and I gave you like that is congruent to that, and this angle is congruent to that angle, and I asked you, are these two triangles congruent? And right there, you do not have enough information to say that they are. Does that make sense? Which, because you don't have enough information to say that they are, that doesn't lead you to the opposite conclusion. Does that make sense? So just because you can't say they are congruent does not automatically make them incongruent. You just don't know. Okay? And that's the idea here. Because of this essentially 90% confidence level, okay, we're going to fail to reject it. We're 90% confident essentially that we should reject it, fail to reject it, but it doesn't provide certainty. It's not 100%. Okay, so it's not a proof of anything. Something that I don't know what value to choose here to see what would change. Basically, what I want to do here is I'm going to choose an alpha value that would maybe put my value over here of my critical region. Okay, so let me see if I can find, let's just go like, I don't know, 15%, see what that looks like. Negative 1.3, it's going to have to be quite a drastic. Okay, so if I say, and this is, I don't think anybody would do this, if alpha was 25%. So I want to be 75% confident with my study, with my ability to reject or not reject. There, if I use 0.25, okay, that means that this critical region is going to move over here to like negative 1 point, or like negative 0.6 or something like that. And now everything over here in green would be my rejection region. And then that Z of negative 0.72 falls in that rejection region, right? Okay. So as I change that, it changes the rejection region, which then could change my decision of whether to reject or not reject. And that is kind of a segue into what we're going to talk about tomorrow, is something called p-values. Okay. What happens a lot of times, because I can change alpha, I can maybe change the conclusion. This is what I was talking about maybe 3 or 4 days ago when I said ethically, you know, if I want to, for whatever reason, my initial hypotheses get written and I have an invested interest and I want to reject this. I want that, I just, for whatever reason, want that to be false. Okay? Well, if I run through all this data and it says, nope, can't reject it. Well, I could, because I understand statistics, jack around with that alpha a little bit, okay, change the rejection region, and then maybe I could reject this. Does that make sense? And then report that it was rejected, okay? And that would be unethical, right? Okay, it would be using the statistics in a deceiving manner, okay? So we don't want to do that. But the idea is to avoid that. A lot of statisticians will, when they provide a study and they give you your hypotheses, they will give the data. Okay, they will give you the z-score of the data, and then they will, from that we create what we call a p-value, and they'll present that p-value to you, and then you get to decide what alphas to choose and what that then does for rejecting or not rejecting. So we'll see that maybe a little bit tomorrow, if not tomorrow, next day in class. All right, so what this question here, does anybody have questions on it? Do we feel comfortable? I know it's the last 2 or 3 days, it's been a lot of the same type of problem over and over, right? Okay. I fear that if I just show you one of these, or we do one of these, and then they change the wording a little bit, that you might get lost, okay? So I tried to give you as many examples that adjust the wording, phrasing, as much as they can, give you situations of two-tailed, one-tailed, right and left. But this question here should hopefully draw a comparison to what we've done in the past with confidence intervals to what we're doing right now, okay? So this might, we're going to jog our memory a little bit here, because it's going to take us back into section 8.1 to do this first part. But it says, research has shown that the amount of sodium consumed in foods has been associated with hypertension, which is called high blood pressure. So the table provides 28 breakfast cereals along with their sodium content, okay? Sodium salt, right? Okay. It says in milligrams per serving. It says assume the population is normally distributed and has a population standard deviation of 90 milligrams. Construct a 99% confidence interval for the mean. Okay. So we know the population standard deviation, okay, is 90. When you know the population standard deviation and you're trying to develop a confidence interval for the mean, if you remember, okay, our mean is going to fall between our point estimate, which is our sample mean, which would be the average of these things, which we'll come up with here in a moment, minus then our error. Then we'll have our sample mean plus our error. Okay. and this is a 99% confidence interval, so a 99% confidence interval, our alpha here would be 0.01, right? Okay. Now, our error, this capital E here, if you remember, is found by taking the Z of alpha over 2 times our sigma divided by root n. Okay, and I'll just jump, I'll come back to this, but jump to section 8.1 real quick. And that's what we're seeing here. If you remember back to this explanation, okay, we did this stuff with the find the z-scores, and then basically taking that equation, turn into inequality, trying to find that central, in our case, will be the central 99% in our question. But solving that for mu will lead to that formula we just created, okay, where the standard error then is sigma over root n, and then we'll multiply that by our z-score to get the margin of error. Okay, guys remember doing that? All right. Now, bless you. So now doing this, so let's go ahead and figure out what E is. So we're going to take E, which is the z-score for alpha over 2. So I'm going to use this alpha over 2. So alpha was 1%, so we're looking at 0.005. Hit enter, and it gives me negative 2.58. Negative 2.58. Now, because this E is going to be placed in here as minus E, and then over here it's going to be plus E, this Z is going to be that positive 2.58. If I don't make it positive 2.58, what's going to happen when I do this is that my interval will be backwards. Just be careful with that. Population standard deviation we said was 90. And then square root of the 28 breakfasts or cereals. So we got that. Now the next thing we need to do is find our X bar, which would be the average of these things, right? Okay. Now don't go ahead and do that, because I think, just to save you guys a little bit of time, I think I can open this in Word and cut and paste those out. All right, so if we go equals average of those, 158.036. 158.036. Are we okay so far with that? So then when we find our interval, okay, it's going to be 158.036. That's our X bar. Okay. Now I'm going to do it this way. I'm going to make E down here and say it's 2.58, 90 divided by square root 28. I don't remember who it was I was working with, but when we did, they were doing this, and they were using lowercase e. Understand, whenever we, and this is all computer programming applications, E is a number. Okay, E is then it's called the natural number, Napier's constant, whatever you want to refer to it. You guys remember talking about logarithms in Algebra 2? You dealt with this as a base, but if I use this as lowercase e right there, like it's not even going to do anything. Does that make sense? Like, it doesn't know what that means. So then when I recall lowercase e later on, it's not going to recall this value that I want. So either avoid it or use a capital E. I'll let this be here my mean. Okay. So then when we do our confidence interval, it's going to be the mean minus E and the mean plus E. So are we okay with that? So this interval is going to be, I'll write it here in red. We said 114.15 less than mu less than 201.91. Or should I write that as 92? All right, so this is where I took that pause. These actually need to be changed. Okay, so let's look at, and they don't all need to be changed. Let's just change this first one. It says, now conduct hypothesis testing using our significance level of 1% to determine whether the mean sodium content per serving differs from the following values. So instead of 165, let's go ahead and use, let's go 110. Okay. So we are going to, what we want to do here is create our hypothesis testing. Okay. We've got H sub 0 and H sub A. And this is saying that determine whether the mean sodium content serving differs from the following values. Okay. So it differs from 110. So I'm going to say that the alternative hypothesis talks about how it differs. So it's not equal to, and we'll say 110. So then that would mean the alternative hypothesis, or sorry, the null hypothesis here would equal 110. Okay. And all I want to do is I want to go through and do some testing on this information. Okay. Now, if we go ahead and construct this, my hope is that we can, once we do one of these, we can maybe quickly come up with the other ones. But we need to find if alpha is 0.01, and this is because it differs here, it's a two-tailed test, right? So we're going to draw a picture of two tails. And this number right here, okay, going with the two tails, remember, we've already calculated this. If I go equals norm.inv, okay, two tails, so it's going to take that alpha of 0.01 and divide it in half. Mean is 0, standard deviation is 1, gives me negative 2.58, right? And that's when I said we already calculated that. That's what we found right there. Okay, so I'm going to put negative 2.58 here. This can be positive 2.58. Okay, and now we're going to run, so those are our rejection regions. Now we're going to run through our data, okay, and see if we've got a z-score, which is equal to x bar, okay, which our x bar was the average of these, okay, and we said that that was 158.036, 158.036 minus mu, which we're saying is 110, over sigma, which we said was 90, divided then by the square root of 28. Okay, so type that information in. Let's clear this out. 158.036 minus 110 divided by 90 over the square root of 28. Oh, 28. Gives me 2.82. 2.82. Okay? So a Z of 2.82. And that Z of 2.82 is going to fall to the right of 2.58, correct? So what do we do in this situation? What do we do to this null hypothesis? If that 2.8 lands there, we reject it. Okay? So I just want to leave that, we reject it. Okay? Just let's go to the next part. Okay? And when we get all three of these kind of figured out, we will then come back and see how these rejections relate back to the confidence interval. So the next thing then is this one here. So hopefully we can just kind of keep the pattern. So the null hypothesis and the alternative hypothesis, again, the alternative hypothesis, because of the way this was worded, would be not equal to 166. And the null hypothesis would be mu equals 166. Okay, the alpha level will still be 0.1, so this is still negative 2.58. This is still 2.58. Okay with everybody? Okay. And really the only thing up here that changes is the mu, correct? So the z-score of this information is going to be 158.036 minus 166 over 90 divided by root 28. So that's what I was saying, that hopefully we could, once we get to B and C here, we could just kind of only have to change that number right there. Okay? And it gives me negative 0.46. Negative, I'll round out to negative 0.47. Okay? And that would be, the red is my rejection, negative 0.47 is going to fall about right there, right? So what would I do there? Not reject. And if we come down to the last one, same idea, 2.58 there, 2.58 there. Okay, now the 220, so my null hypothesis would be mu equals 220. My alternative hypothesis, mu is not 220. Run through my z-score, so be the 158 number minus now 220 over 90 divided by root 28. So again, the only thing that's changing here is the mu out of our z-scores, so make this 220. It gives me negative 3.6, right? So z equals negative 3.6, which that z-score is going to fall right there. So what do I do with that null hypothesis? Reject, right? Okay. Now we haven't made any comparisons yet, but now I want to make a comparison. Okay. Where was the one? Think about our confidence interval. Where is 110 on our confidence interval right there? Is it in the confidence interval or is it outside it? It's outside. So if I've got a number line, so I'm going to go 114 to 201. Okay? That's our confidence interval. Okay? 110 fell out here, right? And what happened when it fell out there? What did we do? We rejected, right? Where does 166 fall in that confidence interval? Be maybe about right there, wouldn't it? So it fell inside the confidence interval. What do we do when it fell inside the confidence interval? We did not reject it. And then 220 would be over there, right? And what do? We rejected it. Okay? So if I were to give you, the relationship we're seeing here is if I were to give you any of these values, essentially with a 1% margin of error, or sorry, 1% level of confidence, or level of significance, get the right word there. 1% level of significance, a 1% alpha, okay, and you develop a confidence interval, then that confidence interval is ultimately the values of mu that you would fail to reject the null hypothesis. Does that make sense? Okay. So my hope is, and I don't think it's always, and I say that they're directly related, or when we did alternative confidence intervals, that leads to hypothesis testing. If you go back to some of the videos and listen, I talk about how confidence intervals build us to hypothesis testing. That is the relation. Thank you. That is what we're seeing there, and that's the connection between the two processes. Does that make sense, everybody? All right. Now, obviously, change the alpha. Okay. Change the level of significance. That's going to change this window here of our confidence interval. Okay. It might narrow it. It might widen it, and then it would narrow or widen the values here that would be open for allowing rejection or not rejection. Does that kind of make sense? All right. I just think it's in mathematics when we come across things that are intertwined, not just to say, hey, they're intertwined, but actually show you and let you see the math kind of play out and see the connection between the two. And that's how you see it with hypothesis testing and confidence intervals. So does anybody have questions? I know we're running out of time, but does anybody have like pressing issues, concerns, worries about hypothesis testing so far? Like if I were to give you a quiz on Thursday, which I am going to do, and it were simply just confidence intervals using critical values like we've been doing, or not hypothesis testing using critical values like we've been doing the last 3 or 4 days, questions like these up here, would we feel comfortable with those? Okay. All right.